So, this is the first definition, okay, from Marty. So it's very different from the point of view of what you are listening right now. So I will start from the bottom. The bottom is a group. After we have hypergroup. After that we have Hvgroup. And we are going to see how to put a natural element in this thing. So it's quite different, and more or less we are going to create a paradox because we want to compute, you know, somebody asks you how to go to the first floor. Okay? And we respond, we answer to him, go to the second floor and go down. But he doesn't know how to go to the second floor. So he said, don't worry, we will get it. So, in fact, here we are at the first floor, and this is the most beautiful part of this way, and because it's quite obvious that it's not used. It's useless. Okay? So don't worry, don't try to apply it right now, especially for the physics. So, you see, I will draw it. I can use it. Yeah, but yeah. Oh, you are a mathematician. You say yes, but without anything. So, in fact, we want this. To do this, you should do this. Okay? From the bottom. But now we are going to do this. Okay? So we are going to be there, before there, before there. Okay, you see? So we have group, hypergroup, Hvgroup. And after that we are going to do this. So it seems to be rather strange. In fact, for the computation, is very efficient. So we are going to prove this. So don't worry about that. The problem, because I use, so is Thomas. By the way, Thomas tried to prove to all the other papers that D is theta. Never mind. Remark this. Okay, so which is a very important point from our point of view is this. Of course, for Thomas, it's only a little theorem. I think that is the most innovative part of the work of Thomas. It seems to be very strange to be a guy of the power and put the weakness of the power. But in fact, for our computation, this word is very important because it has heredity. So, the question is very simple, much more simple, but by the way, Thomas told me that he has done already an introduction for mathematician. So you know, we are working only for simple things, very simple things. So, the question is, if I fix n, then I want to find how many groups of this order there is here, how many hypergroups of this order, how many Hvgroups of this order. At the end, I will find also this, okay, that we want. The problem is quite obvious and very classical here. So we have very small numbers, and the problem in our field is that already with hypergroups we have very, very big numbers. So to imagine a problem, Because even in physics, you are working on something which seems to be quite complex. But at the end, if I ask you, especially in quantum mechanics, can you tell me how many structures like this you will get with a fixed n? In fact, you never answer to this question. Not because it's difficult, but because maybe it's too simple for you. So don't worry, we are here for the very simple things, mathematics. So here, just to put the number, just to remember, we are show here, you see, they are all Hvgroups. So the description is quite obvious. So you have all the elements, of course, and by this element, you can see also what we are drawing with stars. The stars are the hypergroup. So with the stars here, and when you have only two elements, so with only two elements, you get only one group. Okay? With two elements, you get already 8 hypergroups. With two elements, only two elements, you get 20. No? You can see that. So, the only which is a group is this one. Agree? So I put only the matrix in fact. So I do this, and I do the computation, so I will get only one group. If now I am in the field of H group or Martin, and here we are with this, I will get all the stars. No? So I will get H8 hypergroup, only with two elements. So there is a problem we have in mathematics to not only to compute, but to understand what this means. In fact, you mentioned the quotient. Okay, so if you get if you have a group and you get the quotient of the group to the subgroup, wherever you subgroup, you will get the hypergroup. In fact, you will get the hypergroup, which is the stars, not the other one, okay, for the moment. So now, you can see that only with two elements, we have one group, 8 hypergroup, 20 Hvgroup. So it's much more easy to see. If you want to get this one, you will see if the numbers are the same. If the numbers are the same, so you will get this, because you have a natural element. So, the problem is that even for many computers, if you get the order 3, you see? So, we know, it is a result of Chang actually, there exists up to a zone of it, all the things I mentioned is all the time up to a zone of it, okay? So, there are only the Hvgroup of other 3 with a scalar unit. You know? So the problem is that how to find them. So if you can see the list, you will see. So this is a product. You will get in this case what you see here is quite different. I have 3 elements. So I compute, in fact, only the difference. You see? I mean, I mentioned here not only, so I should have this. Okay? I should have this. But the problem is this. If you get, for example, like this, the only difference, here it's obvious, here it's obvious, so this is the important part. You agree? It's clear? Okay, so here I will put only this part, not this part, which is obvious because the element is not. So you will get the Hv group of all the three, and you have here the three elements are those. So the difference is that you have many elements, seems to be there, but in fact our computation, because shown do the previous system, to get that, they do this. To get more order, we do this. The difference is the efficiency in computation. So now we'll try to find the other one, so don't worry about that. Just to see the result. You know, if you want now to have up to isomorphism, Hv groups of all the three with the scalar unit, you will get this number. So, and if you have now, without this constraint of scalar unit, you will get already this number. So, in fact, we have...
Can you please stop taking picture because it distracts from the attention, if you don't mind.
Okay.
We want to hear the thought.
You will have this number, which is quite big. And in fact, for computation, you are going to use many days to have the result. So the problem is that it seems to be easier to do this and after this, but from the mathematical point of view, it's better to do this and to specify this to get this, which is quite strange at the first time, because I will show you why. So here we have a classification. I think it's much more important for you in physics. So here we have the abelian classification, non-abelian. You will get the difference, you see? Abelian are very few. Non-abelian are the biggest part, which is...
Yes.
Okay. And now we have projective and non-projective. The classical, non-cyclic, and you will see that in fact with the automorphous group, if we compute this row, you will get that the biggest part is here. The importance of this computation is not only because they are computation of big numbers, but in fact they show to the theorists, but also to the guy who wants to apply this, that if you get a theorem on one of these guys, the best one is here. So it's very important to get the theorem from a automorphous group with order 6 for the cyclic and for the non-abelian. If you try, you say, I can show you this. I mentioned here, for example, the theorem, and I will say for the abelian Hv group, cyclic, projective, I will get this property, and I will get 1. There will be only one candidate to get all these properties. So the problem is that when you mention a theorem, you want to know how many candidates are satisfying this theorem, which is a very important part, because we are some mathematicians who thought that the important part of their work were in this field, and when we do the computation, we will find only few hypergroups. And on the other part, they thought that it was not very important, and it was the biggest. So you know, if you get a theorem, and the result is only here, and another theorem, and the result is here, for the applied mathematics, it's very different, because here we are more free to find other structures. So, just to show you all this, and you can see now that up to isomorphism, okay, of all the three, this is the number of Hvgroups. So we have more than 1 million structure with only 3 elements. I mention this because many times, you know, in physics, we try to find some properties and to be quite free to choose one of the objects which satisfy this. Here, you have a huge number of objects which are satisfying all the Hvgroups properties. And in this field, in this set, this field, you can choose some of them that you prefer. For example, Professor Santis prefer with the natural element, okay, so it's only a few of them, but they have already this property. But now you can see that if I do the classification of Hvgroup of order 3, even now, the biggest number is here, okay, which is showing something. So we have only few elements here, so you can see that the distribution is not at all equilibrated, and all the time the non-abelian and the cyclic are the biggest ones, with many orders difference, okay, not only the biggest in terms of order. So, in this case, just to show you something, okay, so with Kogiesov, Spartalis and Euclides, they try to find the name very thin hypergroup, okay, so we find 2 very thin. In fact, moreover, at order 3 we get 16 very few. So now we are at order 4, only 4. Don't worry about 5, it's not, cannot use it for the moment. So for the order 4 we use only the abelian Hvgroup of order 4, and you get already this number. Okay? So up to isomorphism. And now you will see the table already for that. Okay, so we've done a partition with the isomorphism group. You can see this. So all the time with this, which is a theorem of Lagrange, we get this number, and you can see the distribution already in this case. So for because we are only in abelian, is cyclic, non-cyclic, and you can see in this case that the biggest number is here. So in the case of the abelian Hvgroup, it's much more efficient to choose a Hvgroup which has 24 as the order of its orthomorphism group than the others, because you are much more free to choose the Hvgroup that you want to compute or use in your application. scalar unit. So we do exactly the same thing. Now we get only this number, which is quite big, in fact. And you will see, in this case, which is with the scalar unit, that the biggest part is at the same place. Yeah. So, which is rather logical, in fact. But the problem is that with this computation, in fact, you can predict the class of Hvgroup you want, and to use them for not only one application, but for many. So, now I put, in fact, only numbers, and maybe you don't see why those numbers are important. In fact, now we can use partially ordered set to understand why we are doing this method and not this one. Okay? So, with posets, it's quite easy to see what we are going to do. So, we get, for example, hypergroup, okay, for the 2. Remember the annotation with the star, so only 8. And we try to classify them in this way. So we use a Hasse diagram. Everything is no, I think. Yeah? So I use a Hasse diagram to classify in the order theory. So I will get a poset. Each dot is a hypergroup, and the operation are inside the other one. Okay? So, for example, this one will be the hypergroup with H. So everything is here. On this side, I will get, for example, a group with only one element. So, with the poset, you will get this structure. You can see that this structure is not symmetrical, not very nice in our words, but this is only a fact. Okay? So here we have a simple order representation. In fact, you can draw here on the page now arrows. So you will prove this. You see, these 2 points are those. So this one is the biggest one. Okay? So now we know the poset of the hypergroup, and we have here a projection. So this representation is only this, and this representation is only this. Okay? So now we want to do the same thing with Hvgroup, but we cannot draw it. I will show you what I mean right now. So, to construct this poset, I can make a table, and I can show that at the first round I will get 2, 1, 3, 1, 1. Okay? So these numbers are the same here. So now we will have the hypergroup of order 3, and we will have a poset which has at its rank 1, 59 numbers, okay, point, at the last only 1. So with this I can draw a poset. It's not used here, but now I will have the Hvgroup. So for the Hvgroup, the result is quite beautiful. Why? In fact, it's due to Thomas, but of course Thomas doesn't know it, okay? As every time, okay? So he creates beautiful fact, and after that, I tell him what is beautiful. Sometimes he agrees. Okay, so you will see what fact, we see what we get. Okay? So now we have a structure which is very symmetrical, very nice, and for painting very aesthetical in fact, because in this structure Thomas put one property, the weak property, which is heredity. In fact, the important thing in computation of the creation of Thomas is the following thing. If you have Hv group, if you put something, it will be Hv group. If you have a group, if you put something, maybe it will not be a group. If you have a hypergroup, if you put something inside, more, so you put more, you get less. With a weakness, when you put more, you get more and more. So the difference here is that, in fact, you can see that from the 5 points, you have all the time something above, which is, in fact, the picture of the heredity property from this weakness. So, in fact, from the weakness of Thomas, we get the power of the poset. This is very important because you can see, for example, don't worry. So, when Thomas is alone, you get that. When he is with others, you get that. This is much more beautiful. You should think about the collaboration in production. So, but of course, with Professor Santilli, we get something much more general, so maybe much more symmetrical in many space. So, the extended we try to extend this result, so I will mention only this category, the hypocomplete hypergroup, which is more or less the symmetrical part of the hyperthin. So you see, if you have the hyperthin, in fact you have only one difference from the group. Here, you have only one difference. You see here, the hypergroup is hypocomplete when all its operations except one are complete. So you will get H all the time except one time. So for this, we have not only properties, so you will get an abelian hypocomplete if you get that, and the number we will get is very small. It's only for order n, this one. So you see, just to apply the same method, you will get a theorem at the end. So for the proof, don't worry, it's written, so I will mention all the time. But the important is that for the hyperstructure, if you do the same thing, and it's a non-abelian hypocomplete hypergroup. So in this time, because similar theorem, so now we get of the n, and this is the number of hypocomplete hypergroup, which is a combination of the two previous. What we mentioned about rigid. Rigid is the hypergroup or the average group which has, you see, a group, an homothermous group which is trivial. So the order is 1. So rigid means in fact that you cannot change some hyperoperation and they are unique in the result. In this kind, you will get this result, so 7 possible cross products here for the quasi group. But maybe it's too restrictive for you. So here you will have the 14 quasi group, so we have to get all the classification and we can compute them. So now with hyperrings. So more or less we'll get the same thing. You remember the definition, so it's obvious. In this case, so they do something like this, and they try to enumerate. So Analyses compute in fact a restricted class, which is the dual Hvgroup. In fact, the dual Hvgroup are very restricted, so we try to generalize this result. Sorry, because I use. So now, some very few propositions which are very important, in fact. So you see, the automorphism group of the hyperring, I can prove that it is only the union of the two objects, okay? So we have this corollary, which is very important for the computation. And now we prove with this corollary and computation that we have in fact 63 isomorphism class of hyperring of order 2, which is quite big, in fact, if you realize that we have only two elements. This possibility from mathematics could be very useful in physics, because you can choose all the time which one what you prefer. Without you see the number, so we have 63. In fact, this is the number with this one with a quotient of 2. So now, if you want to see the important thing, so now we have Hvgroup of order 2, and now we get this number, because they are Hvgroup. Okay? So the table 10 will show you the classification, and now we have the same result for order 3. So you will see that in fact it's very important we have this very big number, but in fact you will see again that the biggest class is the class with the biggest order of the isomorphism group. So it seems to be that this class is all the time the much more interesting class also for application. I can show something about the algorithm. So about the generation of the hyperthreading and partitioning. In fact, we compute candidates, and the important fact is that when we compute this, if we use the weakness property, we know that we can generate them, and we are sure that we are inside. Without the weakness property, when we generate them, we have to verify if we are inside the set we want. So the code is very big. So the partitioning is doing like this. You see the definition. So in fact, we are all the time use the orthomorphism group, which is very important. I don't think that, in fact, even for mathematics point of view, we are studying this very often. So you mentioned about the fundamental relation, you know. I think we should have done something on the automorphism group from the hypergroup or the Hvgroup, which is quite perturbing, because with the automorphism group we are again in the group, but we are again in the group from the hypergroup Hvgroup point of view, which is much more powerful. So the validation and the enumeration, you can see here. The first result we get was from another, which proved that we have 390 999 hypergroup. For the hyper rings, we do the same thing, and more or less we are all the time using this method. From above to bottom, and not from bottom to above. That's why we get all this computation. Okay? So, for me it's okay. You can, of course, answer to some question. But now you have all these things.
You want to continue?
No, that's okay.